Hi guys, good to see you. Mr. Kane here.
Good morning, Mrs. G.
All right. So we have arrived at lucky unit number 13. We are going to do chemical bonding.
All right.
All right, so why do chemicals bond?
Because they like each other.
All right, so some goals for the units. Identify the types of bonds.
And know their characteristics. All right, that sounds easy enough.
All right. Sounds like some memorization. Define electronegativity. Hey, we did that.
Yeah, we
All
just
right.
discussed it.
We already discussed that. That was the last periodic trend we did.
Yep.
And use it to predict the type of bond. Oh, wow, so periodic trends are useful.
How about that? That's amazing.
I wonder if that's one of those things we'll see every once in a while.
Yeah. Periodically?
Periodically. Be able to draw something called a Lewis structure.
Yep, those are fun.
All right, those aren't too hard. Be able to use Vesper.
Valence shell electron pair repulsion theory.
Ooh, hey, that's a mouthful.
The actual geometric shapes of the molecules, because of course we always draw them flat on the board.
Are we doing geometry here? I'm in geometry right now. I'm not sure that I can do this.
This is geometric shapes.
Oh, okay. All right. So square, triangle, circle. Okay.
Yep.
All right.
That's a memorization thing too.
All right. Be able to predict the polarity of compounds. Electronegativity is the ability for an atom in a compound to attract shared electrons to itself. This is familiar, right?
Yep.
All right. So this is just a reminder. In a covalent compound, electrons are shared, sometimes evenly, sometimes not. So in a bond between carbon and nitrogen,
which is a covalent compound, because those are both nonmetals.
Right. You tend to see that nitrogen gets the electrons a little bit more often than carbon.
And since electrons are negatively charged, the nitrogen is slightly more negative than the carbon end.
And just looking at the periodic table here, Mrs. G, I can see why. Nitrogen has an electronegativity of 3.0 according to the periodic table, and carbon has an electronegativity of 2.5.
Correct.
So the one with a greater electronegativity gets to pull in the electrons better.
Yep, those shared electrons find nitrogen a little more attractive than carbon, so they squeeze just a little closer to it.
Very nice, okay.
Well, that one's easy.
In a nitrogen-nitrogen bond where they're sharing two electrons, it's 3.0 and 3.0, they both are sharing equally.
There is no difference in electronegativity, therefore there is no polar bond.
Okay, that's pretty simple. Yeah, I guess in the carbon-nitrogen bond, you're going to get a little bit more negative on the nitrogen end, aren't you? Because the electrons are a little bit closer to it.
Yep, and a little more positive on the carbon.
Okay.
So you get a polar molecule. Ah.
I think we're actually leading into what we want to talk about, polar and nonpolar covalence.
How about that? Ooh, periodic table.
Oh, so quick reminder about the trend before we actually talk about polar and nonpolar. So electronegativity does increase as you go to the right.
Which we said nitrogen had the greater one than carbon, which is verified by the numbers.
So the highest electronegativity on the periodic table I would predict to be fluorine.
Yep.
Right? And since the electronegativity decreases as you go down, I'd predict that the lowest one would be the other F element, francium.
Yep. And the noble gases are technically not included in this trend because they don't
like to bond.
Yeah, well,
it's hard to make them bond.
Yeah, they're inert. They will make molecular compounds, but
most of the time, we're not going to worry too much about them.
Yeah.
Okay, bonds are forces that hold pairs of atoms together and make them function as a single unit. So there are the two main types of bonds, and we should remember this from before.
Right, this is prior knowledge.
There's covalent bonds, where the valence electrons are shared.
Right.
We've said that before. It turns out that there's two types of covalent bonds. There's the polar and the nonpolar.
Yep,
Subcategories. And there are ionic bonds where the metals actually lose the valence electrons.
Yep.
And they form cations, and the nonmetals gain those electrons to form anions.
Yep. And let's see, under the covalent bond category, that includes the metalloids, yeah?
Yes, we're going to consider the metalloids as nonmetals for the purpose of bonding. So the difference in electronegativity is actually what's determining the type of bond. It's not just one electronegativity, it's both of them compared to each other.
Right, it's the difference, literally the difference between the two.
Right, so the math problem is one electronegativity minus another.
Right.
All right. The larger the difference in electronegativity, the more ionic the bond tends to be.
Yep.
Right. The smaller the difference, the more covalent. And as a matter of fact, the smaller the difference, the more non-polar covalent the characteristic of the bond is.
So the difference in electronegativity will give you a number that will determine whether it's a polar covalent, non-polar covalent, or ionic.
Right, and we're about to review exactly what those numbers are.
Good. All right, so difference in electronegativity, that's what the little triangle means, difference in electronegativity, determines if the bond is...
Now, that first one there looks like they're sharing the electrons equally.
Sharing, and it's a very, it's a nice...
I'm thinking this is the center of an atom. That's the center of an atom, and I'm thinking this blue field represents electrons, right?
Electron cloud, and it looks evenly distributed, evenly used, non-polar covalent.
So that one's not polar.
Okay.
Right? So the next one looks to me, this sign here, the sigma, this sign here, the sigma, I think we've seen that before, right?
Right.
Sigma plus, that's a partial positive charge. If we haven't, mark this down as a Greek letter, sigma, and it means partial charge, so partial positive and partial negative. And we can see from the electron distribution here that more of the electron is more so over on the right side here.
So that electron cloud is going towards the right.
Right. So there's a little bit of polarity in this one. Right. There's a little bit of a positive side and a negative sign. So we call that a polar covalent.
Yep.
Notice the reason why it's covalent is because they're still sharing. The electrons are still going back and forth. I can see that because there's not a break here.
Yeah. It's just that they're not being shared evenly. They're more attracted to the right hand atom.
Right. And then in this last one, notice that the electrons don't get shared. They're completely over here on the right-hand atom. So
one is a positive ion, one's a negative ion,
Right. This one's got an extra electron at least, and this one has one less electron than it should. So that's got to be my ionic.
That's ionic.
All right.
For ionic, if the difference between electronegativities is anything greater than 2, then it is an ionic compound.
All right. So I subtract them. If the difference is 2 or more, I say it's ionic.
Correct.
All right. What about polar covalent?
Polar covalent. Do the subtraction. Big electronegativity minus little electronegativity, and you get anything between 0.5 and 1.9, and it is going to be a polar covalent bond.
Okay.
Anything less than 0.4 will be a non-polar covalent bond.
All right.
Which is kind of makes sense. I mean, think about the diatomics. There is no difference in electronegativity, so the bond can't be polar.
So I'm noticing something here, Mrs. G. None of these numbers are negative. So either I'm always subtracting the large number minus the small number, or I just take the absolute value. So if we're trying to calculate the difference in electronegativity between two atoms, such as hydrogen and chlorine, we need our periodic table.
Right.
It has the electronegativities printed in the lower right-hand corner.
We're not going to make them memorize them all?
Well, we probably should. All 118 elements. How about we only have memorize the electronegativity of the first 3 noble gases?
There you go. We could do a whole Moodle quiz on electronegativity.
That'd be awesome. Actually, no, guys, don't memorize anything. Just look on your periodic table and you check what the electronegativity of hydrogen and chlorine is. Okay. So you find out that the electronegativity of hydrogen is 2.1. The electronegativity of chlorine is 3.0. You subtract the 2 from each other so that you get a positive number, and you get 0.9.
Which comes under the category of?
That was a polar covalent, right?
Yep.
Okay, so that falls in the polar covalent range, so I would label HCl as polar covalent, right?
Sodium and chloride.
Sodium and chloride, all right.
Look on the periodic table. We look for the electronegativity of sodium and chlorine.
Sodium is 0.9. Chlorine is
3.0.
3.0. So we subtract 3.0 from 0.9 in a way that gives us a positive number.
Yep.
Or we just take the absolute value when we get the difference. And we get 2.1. 2.1 is greater than 2.
Which is going to make it an ionic character, which we knew.
We kind of knew that already, right?
Yeah.
It's salt. Okay, Mrs. G, now, if I know that it's a metal and a non-metal, can I automatically say it's ionic?
Nope.
Yeah, I have to do the math.
Yeah, the math will actually be the definitive test of type of bond.
Okay, so we're actually expanding our knowledge here. This is something new.
Because like everything else in chemistry, there are discrepancies you're going to come across.
Okay.
You're going to think something's ionic when it's actually a polar covalent.
We're back. We're back.
All right, so this is difference in electronegativity greater than 2.0.
All right, so usually it's a metal and a non-metal, although it's not always.
Yeah,
right?
but we know you can recognize visually. Most of the time you're going to be able to recognize it based on where it's at the periodic table. I mean, we did this first semester.
Right. Okay, so the difference, the metal loses electrons to become a cation, the non-metal gains. We said that already.
Yeah, this is all first semester stuff.
And electrostatic attraction. The thing that's, the bond is formed between an electrostatic attraction between the cation and the anion. In other words,
and
opposites attract.
And it's a strong one.
It's a very, very strong. Matter of fact, I think this is the strongest kind of bond we've got in chemistry, right?
Yep.
Okay. Polar covalent bonds tend to be two nonmetals. One is going to have a larger electronegativity, enough so that the difference is going to be between 0.5 and 1.9. Right?
Electron cloud's going to scoot a little closer to the more electronegative atom.
So the electrons don't get shared evenly. And we call this a dipole.
Yep,
right?
I call it a dipole moment. Same thing.
Okay, dipole moment.
Right.
Sometimes people like to draw vectors instead of those sigmas.
And it always points to the negative end, yeah?
So either way you do this, yes, the vector always points to the negative end. And one thing that I like to try and point out is that in chemistry, we draw a vector with a plus sign on one end to indicate where the positive end is.
Yep.
Right? And this is what is called a polar bond. And the polar bond is created by the sharing of the electrons.
And technically, it's a polar covalent bond, right?
Yes, polar covalent.
Ionic is its own little, don't call it a polar ionic bond. It's not right. That's a crossover.
So nonpolar covalent bonds usually are two nonmetals also. The difference between them, the polar covalent and nonpolar covalent, is that the nonpolar covalent are so small of a difference that it doesn't really matter. So from somewhere from 0 to 0.4. The electrons do wind up getting shared evenly. And this bond is not polar.
So no dipole moment.
No dipole moments. Nope.
No sigma positive, sigma negative.
Nope.
No vector arrow.
Nope. And the bond is created solely by electrons that are being shared, passed in between the atoms continuously. Quick summary of ionic bonds. Ionic bonds.
Ooh, octet. What's that mean?
8. It's like an octopus. The octet is achieved by transfer of electrons. They are made of metals and nonmetals in general. The crystal lattice is made of positive and negative charges. They're held together by ionic bonds.
Electrostatic attraction, yeah.
Right. Solids, usually they tend to be solids at room temperature.
Table salt.
Yep. They tend to have high melting and boiling points, which is why they're solid at room temperature.
Table salt.
Table salt.
You gotta light that baby on fire.
Yeah. Large difference in electronegativity, and they can be soluble, although some of them are not.
Yes, remember the solubility rule.
Covalent bonding.
Ooh, nice picture.
That actually shows the fluorine atom and the fluorine molecule.
In its elemental form, it's a diatomic.
And those are Lewis structures underneath them, which we'll wind up talking about later, but this is a Lewis structure for fluorine. Notice it shows that there's 7 valence electrons. And here's the Lewis structure for the bonded pair, which we tend to draw this way.
Yeah.
And we'll talk about that later. So the octet is achieved by sharing electrons.
That octet again.
Right?
So octet's the nice main category.
So you get two nonmetals usually. They're held together by covalent bonds, which is sharing electrons. Mostly liquids and gases at room temperature.
Which fluorine is.
Nitrogen, carbon dioxide, oxygen gas.
Bromine and iodine are the only odd birds.
Yeah.
Well,
water,
not the only.
Water. Low melting points and boiling points. The difference in electronegativity is going to determine whether they're polar or nonpolar. And finally, they tend to be insoluble, but they can dissolve instead of dissociate if they're polar covalent.
Like dissolves like. Ooh, conductivity of electricity. In order to conduct electricity, charge must be able to move or flow.
All right, and there's a kind of bond that we won't discuss again besides right here. Metallic bonds, they have free-flowing electrons because the electrons get shared around all over the place.
Called electron C model.
So they can conduct electricity because the electrons are free to flow in the sea.
Yeah, it's kind of a weird. It's kind of weird to think your metals are, fluid. Yeah.
The ionic bonds have free-floating ions when dissolved in water or in a liquid form, and that allows them to conduct electricity.
And covalent bonds don't.
Covalent bonds don't have any charges, so they can't move charges around, therefore they can't move electrons around, so no electricity conduction in covalent compounds.
As long as you don't put them in water, right?
Bye, guys.
Bye, guys.